I want to talk about a few theoretical uses of this idea of tangent line approximation. I've said before that the theme of approximation really runs through the course. Sometimes approximation is an applied thing. We're okay with getting a good enough number, but we can also use the idea of approximation in a theoretical way. The basic idea of this is you have a function. It's a nonlinear function, probably. You don't know much about it. You'd like to learn about it. First, you pretend it's linear. Then you take a look at that linear function you get that's supposed to be close to your function. That's called the linearization. You try to see what can be said about that linearization. Can you understand it? Well, we know that linear functions are easy to understand, so the answer to that question should be yes. Then you cross your fingers, you hope, you pray that that approximation is good enough. If it is, boom, you learn something about your original function. Okay, so what are some questions you can ask about a function? A very basic question is the function increasing or decreasing? If I increase the input value, does that result in a positive change or a negative change in the output value? That's the most basic fact you can know about a function. The notions of increasing and decreasing make sense for any function, but for a linear function, those notions are really, really simple. What does an increasing linear function look like? It's just a linear function with positive slope, and a decreasing linear function is one with negative slope. So for linear functions, it's very easy to check whether you're increasing or not. You compute the slope, you check to see whether that's positive or negative, and you're done. If the approximation were good enough, what this allows us to do is to translate the notions of positive slope and negative slope back into a statement about f. F prime at c is the slope of the tangent line. So if f prime at c is positive, that means the tangent line is an increasing function. If f prime at c is negative, that means the tangent line is a decreasing function. And if the tangent line approximation is good enough, that should mean that if the tangent line is a decreasing function, so was the original function f. So I have left out step 3 here. So let's take a look at some pictures that will hopefully convince us that the tangent line approximation is good enough for this purpose. That is to say, the tangent line and the graph of f are close enough together that if the tangent line is decreasing, so must the function be, and if the tangent line is increasing, so must the function be. Okay, so this is a gadget I built in GeoGebra. We've got a function here. If you want to play around with this yourself, there's a link on Canvas. You can go ahead and type in any function you want there. Investigate your favorite function. I give myself a function with some ups and downs to make it kind of interesting. What you can do here, you can drag this point C around. As you drag it, you can see the point we're computing the tangent line at. The tangent line there is that black line. Changes. So let's just take a look. We've got a tangent line there, and we're going to pick A and B. Those determine our secant line. And as you slide them around, you can see it's not the case that all secant lines have to agree with the slope of the tangent line in sine. Right? So you see here we have a secant line that's decreasing, whereas the tangent line is increasing. But I think it's pretty clear that if you get A and B close enough to C, well, as long as A and B are close enough to C, this red line has to be going up, right? It has to have positive slope. So hopefully that convinces us of that. Let's take a situation where the tangent line has negative slope and see if it holds there. Move over to here. And let's see. Yeah, you can see as long as I get close enough, all the secant lines within a certain range of C also have to have negative slope. Let's go ahead and put A right there at C. And then as we move B, you can see what's happening. This secant line actually looks like it's looking more and more like the tangent line itself, not just in slope, but they're actually looking to be like the same line. Yeah. Notice as A passes B there, you can see it flickering. That's because when A equals B, there's no line at all, because A and B are the same point, and to give a line, you need 2 points. Okay, so we've convinced ourselves of this. If you look at f prime of c, and that number is positive, then the function should be increasing near c. If f prime is negative, then f is decreasing near c. Now, besides f being increasing or decreasing, another thing you can say about a function is it constant? Right? We normally don't think of constants as actually being functions, but they are. You just, whatever input you give me, I give you the exact same thing in the output. That's a really important thing to know about your function. What's the corresponding notion for linear functions? In other words, when is a linear function constant? That's exactly when its slope is 0. So the calculus translation of that is that f prime equals 0. Now we should be a little bit careful in stating this fact about derivatives. If the derivative is 0 on an entire open interval, on every point in that open interval, then f is constant on that same interval. This is a little bit different than just checking the derivative at a single point. Here you have to check it at every point of an open interval. But if you do and you get 0, then f is constant there. Of course, those aren't the only two things you can check. Increasing versus decreasing or being constant. There's lots of other stuff, but that gives you the flavor